Today we're tackling a Leetcode problem called minimum cost walk in weighted graph. It's a hard-level problem, but we'll break it down so it's easy to understand. The problem describes an undirected weighted graph, which just means a network of nodes connected by edges, where each edge has a cost associated with it. We are given the number of nodes, a list of edges with their weights, and a list of queries. Each query asks for the minimum cost of a walk from a start node to an end node. A walk, unlike a path, can revisit nodes and edges multiple times. The really interesting part is how the cost is calculated. It's the bitwise and of all the edge weights in the walk. If there's no walk between the specified nodes, the answer is -1. Let's understand with provided examples. Okay, let's look at the first provided example. We have 5 nodes and 3 edges. The first query asks for the minimum cost walk from node 0 to node 3. The explanation shows a walk 0 to 1, 1 to 2, 2 back to 1, and finally 1 to 3. The weights are 7, 1, 1, and 7. The bitwise AND of these weights, 7, AND1, AND1, AND7, is 1. The second query asks for a walk from node 3 to node 4. However, there's no connection between these nodes, so the answer is -1. In the second example, a walk from node 1 to node 2 is requested. It is possible to go from node 1 to 2 using an edge with cost 6, back to 1 from 2 via edge with cost 1, and go back to 2 with cost 1. Calculating bitwise AND of 6, 1 and 1 we get 0. It is the smallest value we can get from walking these nodes, because any path and walk between nodes must consist of some edges. Here's how we can solve this using the Disjoint Set Union or DSU data structure. First, we initialize 2 lists, parent and component underscore level. The parent list keeps track of the parent of each node in our DSU. Initially, each node is its own parent, meaning each node initially forms its own set. The component underscore level list stores the bitwise AND of all edge weights within a connected component. It is initialized to 0 for all nodes. Then we have 2 helper methods, find, which finds parent of the given node by using path compression, and union, which combines 2 components into 1. In the union method, we merge components by performing bitwise OR on current level and weight of current edge. After processing all edges and building our DSU, we iterate through each query. For each query, with source S and target T, we see whether these nodes share the same component with method find. If roots are different, there is no path and therefore no walk. The result is -1. If the 2 nodes are not connected, we append -1 to the result. Otherwise, they belong to the same component, and we use component underscore level for that component which holds the minimum cost. Finally, we return result answer. The time complexity is O, E plus Q, alpha n, where E is the number of edges, Q is the number of queries, and alpha n is the inverse Ackermann function, which grows very slowly, and can be considered almost constant for practical input sizes. This complexity arises from the union and find operations in the DSU. The space complexity is oxygen mononitride because we use arrays of size n to store the parent and component level information. Let us examine another solution. Here, we use breadth first search, or BFS. First, we will construct an adjacency list to store our graph structure. For each edge, we add a corresponding entry. Then we have to build component underscore ID and component underscore level arrays, and initialize the current ID. Now we define the BFS function. It takes starting node as parameter and sets up Q, current component underscore ID, and level variable. BFS will help us to determine the connected components of graph. For that, we're traversing neighbors of given nodes, marking nodes with current component ID if they weren't visited. The result is stored inside of component underscore level. Then we use BFS to find all connected components and store their bitwise AND levels. Finally, we loop through the queries, similar to previous approach, finding if nodes belong to same component. If not, append -1, otherwise append level of current component. Let's analyze complexity of our BFS approach. The time complexity is OE plus N plus Q. Building the graph takes OE time. The BFS traversal visits each node and edge at most once, taking ON plus E time. Processing the queries takes OEQ time, so the overall time complexity is OE plus N plus Q. The space complexity is OE plus N, because we store the graph as an adjacency list, OE, and use arrays for component IDs and levels, ON. Now, here's a solution using depth first search, or DFS. Similarly to previous approach, we're constructing an adjacency graph, initialize arrays to track the component ID of each node, and to track components level. Then we are defining a DFS function. Inside of this recursive function, we assign current node to its component, perform bitwise OR for component level using current edge weight, and recursively visit unvisited neighbors. We loop through all nodes in graph and find all of the connected components. Then for each query, just like before, we return -1 if no path exists. Otherwise, we obtain answer from stored component level values. The time complexity here is ON plus E plus Q. Building graph is OE. DFS traversals will visit each edge and each node, so it will take ON plus E, and processing Q queries will result in OQ complexity. The space complexity is ON plus E. The graph takes OE space, and the component ID and level arrays, along with the recursion stack for DFS, take oxygen mononitride space. That covers 3 different approaches to solving the minimum cost walk-in weighted graph problem. We saw how to use disjoint set union, breadth first search, and depth first search. I hope this was helpful. Let me know in the comments if you have any other problems you'd like to see me cover in this series. Don't forget to like and subscribe for more Leetcode explanations. And if you'd like to help me continue making these videos, you can donate at buymeaboba.com, link in description. Thanks for watching.